Hello, Alice, are you ready?
Yeah, I'm ready. I'm here.
Okay. Yes, good morning, good afternoon, and good evening. Welcome again to this World River and Delta System Source to Think webinar series. And this is Paul Liu from NC State University. This webinar series is co-sponsored by NSF, NC State, Louisiana State University, State Key Lab, Estuary and Coastal Research in Shanghai, and Utrecht University. So today is our great honor to invite Professor Alice Lefebvre from University of Bremen. Come here talk about morphology of estuary dunes, example from Weser Estuary, Germany. And as always, before I introduce Alice, I would like to mention all our previous talk since the pandemic, almost 120. This talk, will be 120. So they have archived on our YouTube channel, also on Bilibili station. So feel free to use them. At the same time, we also have a Source to Think YouTube account. So please feel free to follow us. We will make that webinar talk, publication, conference news through this channel. And next week, same time, is not 15, it's my fault. I forgot to change this, should be 2022. And next Wednesday, Dan Bean from Colorado School of Mines will come here talk about the desert of the deep, the bottom current drawing. So from the thinking part. So Alice, as I mentioned, is a scientist in University of Bremen, and the MARUM is the stand for English, is the Center of the Marine Environmental Science. She graduated from University of Bordeaux, France, get her bachelor and master degree, geology and oceanography, then as a PhD from UK University of Southampton, studied the bed roughness over the vegetated bed. And then is a postdoc at Bremen, associate scientist, and now is the Cluster of Excellency, the Ocean Flow program. So her research mainly focuses on interaction between the hydrodynamics, geomorphology, and the sediment dynamics, mainly in the shallow water, river, estuary, and the coast. So today, she will give us a very interesting talk about large dunes in a river estuary. So Alice, now I'll give the floor to you, and you can unmute and
Okay, so here I am. I hope you can see my screen now.
Yeah, very good.
Very good. Okay, thank you so much for having me here. It's a real delight to be giving this talk. I watched also quite a few of the previous talks, and I thought it was very interesting. I'm very happy, Paul, that you are willing to organize those talks. And I would like to really encourage everyone to sign up to give a talk. And I know Paul is very keen on bringing some diversity in the talks as well, and I would really like to encourage that. You don't need to be a professor to give a talk like this. I'm also not a professor, I'm only a scientist, and it's good to be here. Yeah. So today I would like to talk about the morphology of estuarine dunes, and especially from the Weser Estuary, which is in Germany. So that's what I'm going to be talking about today. I'm going to first introduce the underwater dunes. Then I'm going to talk about the Weser Estuary, because I think it's quite an interesting estuary. After this, I will come really in the deep of the subject about the Weser Dunes morphology, and then I'll talk a bit about Geomorphica, which is Diamond Open Access Journal that we are in the process of creating right now. Okay, so what are bedforms, and more specifically, underwater dunes? Bedforms are features that develop at the interface of a fluid and a movable bed as the bed material is moved by the fluid flow. So they're very much in the middle of this geomorphological loop. So you have fluid dynamics, so water which is moving and which is putting the sediment in movement and transporting the sediment. And if the conditions are right, bedforms are formed. And what's important is that then the bedforms are going to influence the hydrodynamics very, very much. So it is very much a cycle. And we talk about bedforms in general. There are several scales of bedforms. The smaller scales are ripples. And then if you go to the very large scales, you may have things called like sediment waves or banks, things like this. And in these talks, I would like to focus on dunes. You may know dunes from deserts. And in the deserts, you have a lot of sand and a lot of wind. So you create those very large dune fields. And here I put those photos because they're quite interesting. Here you can see just those, a field of dunes with really many of them, and that they're not all, straight dunes. So they're not two-dimensional dunes. With this one, what I like to see that you have some little ripples which are on one side of the dunes. So that indicates that you have some special conditions and that it's not all symmetrical, those dunes. And here I really like to see the sand which is flying here at the crest of the dunes. Okay, so that's in deserts, but I don't work in deserts. If you ever want to know more about the characteristics and what can be the same or different between desert dunes and underwater dunes, you can have a look at the work from Julia Cisneros from the US, who is working on that. Today, I would like to talk to you about large dunes in water. So like in desert, you have a lot of sand and a lot of wind, and that creates big fields of dunes. In river, estuaries, tidal channels, and continental shelves, you have also a lot of sand and some strong currents. So large dune field can develop. And here you have two images from bathymetry. And on the left, this is from the Dutch continental shelf. On the right, that is from the Knudedyb tidal inlet in Denmark. And we're going to talk about this one again a bit later. And yeah, this is just to illustrate that it's really often a field of bedform which develops. Still, we can also recognize a few differences between these two images. First, there is a difference in scale. Here we are on a kilometer scale, and here we are like 10 times smaller. Yeah, that's 200 meters instead of 2 kilometers. And also we may recognize some differences with, especially here, I mean, that's higher resolution, but we can see that we have some bigger dunes and also some smaller dunes. So there may be different scales of dunes which are happening at the same time. And that is something quite important in underwater dune research. So there are several types of classification of dunes, and there are lots of different names that people still use about dunes. I would like to just introduce how I classify them. And I recognize three different types. And the first type would be dunes which form in river and flumes. And there the currents in unidirectional, it's going only in one direction, and it's constrained either in the flume or in the channel. Then you have, there may be dunes in estuaries and tidal inlets, and here it is again constrained, so we are just in a channel, but the currents are going in two directions, and depending in an estuary there will also be the river flow, and in a tidal channel there may not be. And finally, you have the marine dunes, which are also often called sand waves. And here we are in an open environment, so there is no constraint on the side. There is really the space on the side to develop those very large fields of dunes. And you have the tidal currents, but also there you have the influence of the waves, which might be important depending the depth and how big the waves are and when those waves are created. So I think all three are super interesting. I would, encourage everyone to study all three of them. Today, I am going to focus on estuaries, on estuarine dune. If we go back to some very basic definitions of dunes, until now, we're looking at the dunes from looking up and looking down at the dunes like this, and now we're looking at the side. So if we take just a slice through the bathymetry and we look at one dune, the two lowest points are defined as the trough, and the highest point is the crest of the dune. And here that's an example where we have one large primary dune, and then on this side we have also some smaller superimposed secondary dunes. Now, the most basic measurements that we do of those dunes is to calculate their height and their length. And then if we know the flow direction, we can also define the lee side, which is here. That is the side which is sheltered from the flow, and the stow side, which is the side facing the onward flow. And usually in rivers and in all unidirectional environment, the stow side is quite gentle and the lee side is quite steep. And here it seems to be like really quite steep, like, maybe 50 degrees or something. However, it is definitely not as steep as we always put them on our screens. I think it's all geoscientists. We have a tendency to put extreme vertical exaggeration, and geophysicists definitely do that a lot as well. If you look at seismic data and things like that. So let's, it is definitely not as steep as it looks. The steep side is usually at maximum 30 degrees. And it is 30 degrees because that is the angle of repose of sand in water. So if it gets more than 30 degrees, there's going to be an avalanche, and then it's going to be, go down until it is at least at maximum 30 degrees. And those simple shape, so-called angle of repose, bedforms or dunes, have been widely studied, especially in the flume, because they form in the flume and they are also often found in small rivers. Over such bedforms, the flow, which is going so in this direction, over the crest, the flow separates, and there is a big eddy which forms here. So there is a big reverse flow which forms with the flow over the lee side going in the opposite direction to the main flow. And there is a big turbulent wake which is created. So it's very high turbulent kinetic energy over there. And that creates a lot of bedform roughness. So it's taking energy from the flow, all that turbulence. And that's very important because then that's going to impact a lot of different things. So for example, in rivers, that impacts the water level, and that impacts, of course, sediment transport and all the hydrodynamics. However, we know now that a lot of dunes in large rivers actually are really not that steep. So they have a lee side which are 15 degrees or even less. And that is important to know because when the lee side is less than 15 degrees, there is no flow separation. So you don't have that big eddy which forms, and you have only very little turbulence. If the flow if the lee side is between 50 and 25 degrees, there might be a small flow separation, which forms and a bit of turbulence, but definitely not as much as over the angle of repose bedforms. Now I'm going to talk about estuarine bedforms today. So this time we have tidal flows going in one direction and the other. And I told you already, we have those small superimposed bedforms, and those ones are small enough that they usually reverse with the flow. The large bedforms, they keep their shape. They keep their shape with the tidal flow. So they will, the steep side is going to stay on this side and the gentle side over here. However, the flow is reversing. So the lee side is going to reverse. And that's important because in this example, during the ebb, we're going to have a steep lee side, whereas during the flood, we're going to have a gentle lee side. And that means that the roughness and all the sediment transport and the interaction with the hydrodynamics is going to vary very much during the tidal cycle. So again, in this example, during the ebb over the lee side, we're going to have that flow separation and the big eddy which forms with the strong turbulent wake. So we're going to have a high bedform roughness. Whereas during the flood, there is over the very gentle lee side, there is no flow separation and no turbulence which forms. And sometimes there is just the crest of the bedform, which might be steep enough to create a small flow separation and turbulence, but not very much. So there might be variations in roughness depending on the tidal phase. And that is something that I looked at in that tidal inlet, in the Knødup tidal inlet in Denmark that I showed you at the beginning. Okay, so that was my introduction on underwater dunes. And just to remind you, they are very much in that morphological loop where we have the hydrodynamic sediment transport and the morphology. And especially the bedform morphology, the dune morphology is very important to see the whole interaction between those three elements. Now I would like to talk to you about the work that I did on the Weser Dunes, and that was published in Earth Surface Processes and Landforms. So if you want to know a bit more about my work, please have a look at the paper. And I would like to take the time to acknowledge as well the work of my co-authors on the paper. So Gerald Herrling, Anna Zont, Marius Becker, Knut Kremmer, and Christian Winter. Now, the Weser Estuary, you can already maybe hear how I say it. It's situated in Germany. That's why we call it Weser and not Weser. And it is more specifically in northern Germany. So this is the North Sea. Here we have Germany. Over here we have the Netherlands. And here we have Denmark. And this is the Weser Estuary. And this is called the Jade Bay, which is a large tidal bay. Yeah, in the Weser, we have a few important places. And here first, I wanted to mention that we have those numbers, which I have put on the map. And those are the official kilometers along the waterway. And I will be using them. You will see them in the different plots. So it starts in the city of Bremen and goes into the North Sea. An important place in the Weser Estuary is the port of Bremerhaven, which is Europe's second largest terminal for cars. And it's like a lot of cars which are going through here. So of course they need good waterways. They need to ensure that they have a good channel, which is deep enough for big boats to go in and out. And also, yeah, it's a lot of logistics with the ports. We also have the beautiful city of Bremen, which is here. So that is really at the upstream part of the estuary. It's a really totally beautiful city. And if you're ever in northern Germany, I would like to encourage you to visit it. We are only an hour from Hamburg or Hanover. So it's very easy to come here by train or by plane and visit the city. And the limit of the tidal influence is here at the tidal weir, which is called in German the Weserwehr, where you have a big weir which blocks the tidal wave. So we have the tidal influence coming from the North Sea into the estuary up to here. And I would like to tell you a tiny bit about the history of the estuary, because I think it's quite interesting. It's not 100% related to my work, but I think hopefully you also find it interesting. So Bremen is a beautiful city, and it's an Hanseatic city, it's called. And you can see it's the old city center here is very much with the river, because the League of Hanseatic Cities was, there were several cities it started in northern Germany between the Baltic and the North Sea, with cities like Lübeck and Hamburg, and then over 100 cities joined the League. And they thought that by working together, they could be stronger to do a lot of trades. So it is cities which in the Middle Ages were very keen to have good trade. And in order to have good trade, you need to have a good river where you can transport things by boat. In the Middle Ages, that used to be completely fine. And the Weser in Bremen was around 8 meters deep. So it was definitely big enough for all the boats of the time to come and do all the trades in Bremen. However, as agriculture started to expand, there was less and less forest around Bremen, and so a lot of erosion. And then there was a silting up of the lower Weser, so a silting up of here the channel in Bremen. And so the ships could no longer reach the harbor in Bremen, and little by little, the harbor moved more and more downstream until it arrived in Bremerhaven in 1830. And then at that time, so it was in Bremerhaven, which, I mean, that's okay, yeah. But then the ships were unloaded and goods were transferred by smaller boats to Bremen. So you see, now it was only the small boats which could come to Bremen, because over there it was very shallow at that time. And that was not very good for the trade. So they thought, okay, how can we make large ships actually navigate the Weser all the way down to Bremen? And that's where that guy, Ludwig Franzius, you can see him here, got an idea. And so he was the Bremen's shipbuilding director. And he had the idea of what's called the Weser correction. First of all, he spent 12 years just collecting data on the river. So everything, like he did like super good mapping of the river and did a lot of measurements in the river of the whole bathymetry, but also the currents, the water volume. Like it's crazy, because at the time, of course, they didn't have a multi-beam echo sounder to do that kind of thing, and ADCPs and stuff. So it's crazy work that he did. And then between 1887 and 1895, there was the work for the so-called Weser correction. So for this, they removed 30 million cubic meters of sand from the riverbed. They cut the channel to 5 meters. They cut a lot of new channels, and that you can see over here. Over here, we had, for example, this was the main channel, and this was meandering. And Ludwig Franzius thought that it wasn't so good to have so many meandering channels, so it just straightened the channel and made this one the main channel. You can see over here as well, for example, a big meander which got straightened. Okay, so he did all that work to have one long straight channel with smooth bank, which was becoming increasingly narrow, and really directed the flood flow up to Bremen. Why did he do all that? His plan was for the ship to ride on the tidal wave from Bremerhaven to Bremen. So he had the idea of completely changing the whole hydrodynamics in the Weser. And I would like to look at this one. So this is showing the tidal elevation along the river kilometers in the Weser. And here that's kilometer 0. So here we are in Bremen, and 120 were in the North Sea. And if we look in 1882, that's this orange line, the tidal elevation was around 3 meters in the North Sea, and increasing a bit up until mid-estuary, and then it was being slowed down, and we had only 10 centimeters of tide in Bremen. And what the Weser correction did was to remove all that part where the tidal wave was being slowed down. And in the contrary, the tidal wave would just be amplified through the whole estuary. So there is a shoaling of the tidal wave through the whole estuary. And we go from 2.8 meters in the outside of the estuary up to over 4 meters in Bremen. And that means that now the big ship, they can just ride with the tidal wave and ride with the high water all the way to Bremen, and then they have enough water depth to come to Bremen. So I think that's quite extraordinary, yeah, to change an estuary that much, going from 10 centimeters of tide to 4 meters, just to enable trade, basically. Yeah, I think that's quite crazy. So yeah, now just to present a tiny bit more the estuary. If we look at the depth that we have now, so yeah, if we look at the estuary now, and you can see how straight it is, yeah, whereas it used to be a meandering river, and now, especially here, that got completely straightened. We go from around 5 meters of depth in Bremen to 12 meters in the middle part, and then increasing to 20 meters. And here I can already tell you we have a lot of dredging because of the port of Bremerhaven. They want to make sure that we have enough water depth for all the boats to go through. If we look at the sediment, it's a bit muddy around Bremen, and then it's mainly sandy apart around Bremerhaven, because that's where we have the estuarine turbidity maximum. And so we have a lot of cohesive fine sediment, which is being trapped around Bremerhaven. And that is also, that estuarine turbidity maximum is also linked to the fact that this is where the mixing zone is situated. So in the North Sea, we have, of course, salty water, and coming from Bremen, we have the fresh water. And here we have still fresh water during most of the estuary. And around Bremerhaven, we have the mixing zone where we have brackish water. And then we have the tidal range, which is increasing from 3 meters in the North Sea down up to 4 meters in Bremen. And if we look just quickly at the bathymetry along the estuary, we can see dunes. And that is something that we knew already, that we have dunes, because the authorities are not so happy about the dunes. They need to spend a lot of money, 8 to 20 million per year, 20 million per year, in order to dredge the estuaries, in order to have enough depth in the channel for ships to go through. And this is done in two main ways. In the outer estuary, so here that's a picture from around here, we have dune fields, and over there they use the normal technique, which is to use a trailing hopper suction dredger, which is just sucking everything from the seabed to make it deeper. And that costs a lot of money. You can see it's a big ship, and then you have to take the sediment and put it somewhere else. That costs like millions. In the inner estuary, so between basically in that part around here, they used what's called water injection, and there it's just a much smaller ship which comes and which injects water which is flowing very fast and which erode the crest of the dunes. And the idea is that once it is eroded, the crest, then they deposit in the trough, so it's just to flatten the dunes. So as I said, we kind of knew there were dunes. However, we didn't know exactly the bedform presence and characteristics along the estuary. And we also didn't know if there were differences in times of high and low discharge. So we wanted to look at that. And we were also quite interested in the bedform asymmetry. Until now, it was always assumed that the bedform were all ebb asymmetric bedforms with their steep side on the ebb side. But yeah, we wanted to make sure that it was really so, because then that has some influence in terms of calculating the roughness in the estuary. And especially I was quite interested in the detailed morphology of the bedform, seeing if they have a portion which is steep enough so that we get flow separation and recirculation. Okay, so the methods that we used, we analyzed some data, and we're very, very happy that the local authorities, that's the Wasserstraßen- und Schifffahrtsamt Weser Nordsee, notice that you get 3 Fs in a row in that word. They provided us with some grid bathymetry with a grid size of 2 meters along the waterway. So 100 meters, so we had 200 meters wide data along the whole waterway, so around 110 kilometers we had. Nearly every month they have to look at them, to collect data 10 times a year along the estuary, and I analyzed that for the years 2009 to 2013. And that's an example of what the data look like. And from this, I implemented a method to detect the crest line and trough lines. That's what you can see in those black lines and white lines. And from this, I could detect also the bifurcations and the steep portions. So that's wherever the angles are more than 15 degrees. And then I also looked in a bit more detail at the bedform characteristics. So for example, I calculated, of course, the height and the length, the asymmetry, the mean and maximum angles, and the presence and position of those steep portions. Let's dive in directly in the results. Here, once again, we have the estuary, and in red, I put where I found that there were where I found that there were bedforms. There were dunes. And there are three main bedform fields. There is this one, which is by far the most impressive. Yeah, so between kilometer 10 to 55, it's just the whole place is just covered with dunes. Then there is the estuarine turbidity maximum zone, and here sometimes there are a few dunes, but not really as much as in the other bedform fields, and that is because it is known that when there is too much cohesive sediment, the dunes don't manage to develop. And then there are two more bedform fields here and there, and over there is a lot of dredging. All in all, the dunes have a mean height of 1.4 meter and a mean length of 39 meters with a height over length ratio of 0.01. For those who know bedforms, it's actually quite steep. It's a lot steeper than we thought. Yeah, it's not like the marine dunes, which are like sand waves, which are usually a lot flatter. Here we're actually talking about like real kind of steep dunes. And now, although there is a lot to say about the other two bedform fields, I will concentrate on bedform field 1. And first of all, I would like to look at the angles. So here we see along the Weser kilometers, so between Weser kilometer 10 and 55, the ebb lee side angle and the flood lee side angle. And if we look just at the mean angles, the average mean angle are only 5 and 7 degrees. So that's, although I said that they're quite steep, even those steep bedforms have actually, on average, a very low angle. And even the average maximum angle is only 9 to 13 degrees. So all in all, we can say that we have here low angle dunes. And just to show you, because we always have so much exaggeration, and here I'm showing you again a dune with an angle of 45 degrees. In reality, if we don't put any vertical exaggeration, the dunes look like this. So they're actually quite flat. But what's really interesting and what was really a surprise for us is the bedform asymmetry, and that is varying along that bedform field. So in the upper part, we actually found some flood asymmetric bedforms, which then the bedform then became symmetric. And finally, there was those ebb asymmetric bedforms, which we expected to see everywhere. And we expected to see them everywhere because we know from measurements along the estuary that the mean and maximum ebb currents are always stronger than the mean and maximum flood currents. So what's happening is that there is a very complex interaction between the tidal currents and the river flow, and that's why we have those variation in asymmetry. And we have a few ideas what's happening, but we still need to work on that to come up with a proper description of why we have those variations. Now, I also looked at if there were some differences in terms of high and low discharge, because we know that here we are in an estuary, the tidal currents are dominant, but sometimes if there is a high discharge, there is a lot of river water which is coming and which is likely to change the hydrodynamics. So here you can see the graph showing the discharge during the 5 years that I worked on the data. And it's quite typical. In the winter, we have some high discharge, and then in the summer, we have some low discharge. So that happens during the 5 years. In gray now, I show a shape highlighting the mean morphology of the bedforms. And that is how they are in terms of high discharge. So the bedforms are more ebb oriented, and they are also a bit longer, we found, than in times of low discharge, where the bedforms are all a bit more towards the flood. So we have changes in the bedform length and the asymmetry, and not so much with the height of the bedforms, which was again a bit of a surprise. We expected more of a change in the height. And of course, the angles are also changing depending on the discharge. And that has strong implications in terms of sediment transport and roughness. And sediment transport, basically, that's telling you that in terms of low discharge, here it's likely that the sediment is actually transported upstream. And in terms of low discharge, we are going to have a lot of sediment transported downstream. So again, we're still working on that, what the exact implications are in terms of sediment transport. And here I just want to say a few words, the implication it may have in terms of roughness. Because I told you I look at those steep face presence, and here the steep face is wherever the lee side is steeper than 15 degrees. And from my previous work, I know, I think that if the lee side is steeper than 15 degrees, there is flow separation and turbulence and a lot of roughness, which is created. I know the steep face presence along the estuary, that's again the estuary, the river kilometers. And in terms of high discharge, we have mainly that type of dune where the steep face is only on this side of the bedform. And then in the upper part, it's mainly relatively low bedform, which do not have a steep face. Whereas in terms of low discharge, we have quite a different picture, and we have a lot more dunes here. We have a flood-oriented steep face. We have then here in the middle, some bedforms, we actually have a steep face on both sides, or also places where we have a lot of flood-oriented and flood steep face bedforms and ebb steep face bedforms, and a lot less which have this ebb steep face, and here a mix again. So it's all a lot of variation, basically, that we can see here. And here that's just a calculation. I haven't actually managed to say exactly what the implication is going to be, how we can then parameterize the roughness in the estuary. But what I would like people to remember is that the roughness is very likely to vary depending on the tidal phase, and also depending on the river discharge. And of course, all those variations are also be varying depending on the position along the estuary. So it shouldn't be that one roughness can be used for the whole estuary the whole time. One last thing that I would like to talk to you about those about the dunes are the shape. And here I come back to the work that Julia Cisneros did now 2 years ago in several large rivers, and she calculated the position of the steepest angle along the dunes. You can see an example here of the very well-known Parana bedforms. And what you can see directly looking at them, they have quite a flat crest. And what Julia calculated is that the steepest portion is situated here in the lower half of the bedform. And that makes sense, yeah? We have river flow, it's flowing like this, and then it's eroding the sediment here at the crest and transporting it, and it's depositing here. And if it's too steep, then it's avalanching and things like that. So flat crest and the sediment moving in this direction makes sense. What I found out for the Weser estuary bedforms is that we have a completely different shape, and that is quite obvious when you look at that plot, where we see here the depth as a function of the distance, as a function of the depth as a function of the distance. So we see the Weser dunes, and they are quite pointy. Yeah, they have sharp crests. And definitely, when you look at the data, then you can calculate that the steepest slope is situated close to the crest. And that is because we have a tidal flow, which is making the crest move back and forth. Now I found that out. I thought, okay, am I the first one to notice that? Yeah, of course, I'm not the first one. And Dalrymple and Brodes, in their very good reviews on estuarine dunes and bars published in 1995, already noticed that. Yeah, and they wrote whole paragraphs about that, and other people have noticed it. So it's not just in the Weser Estuary, it is something which is happening in most estuaries in the world, it seems. And here I plotted some data from that Knudup tidal inlet from Denmark, where we can see a bathymetry that we took during a whole tidal cycle along the dunes. And I know it's going a bit fast, so let's wait. High water, now during the ebb, you can see the crest here is moving in the ebb direction, and then it's moving back in the flood direction. Please note that those secondary dunes are reversing completely with the currents as well. And what's interesting to see is that this part is hardly moving in the end, yeah? So it is really the crest which is moving back and forth with the tidal flow, and that's why it gets all pointy like this. And again, here, that's just to show you without the vertical exaggeration that it is not as super steep as we make you believe. So yeah, I think it makes sense that in unidirectional flow, we have those flat bed forms, whereas in the reversing flow, we have those pointy bed forms. And then it made me think, okay, but actually the ripples, we kind of have the same thing, don't we? Because if we look at current ripples, they're also flat and then quite asymmetrical, whereas the wave ripples are very sharp crested and quite symmetrical. So I don't know, I haven't done any work on that yet, but I think it is something to explore. Yeah, I'm very interested in the different scales that we have, because here we have the waves and here we have the tidal wave, and what is the impact and the interaction, yeah, between those things and sediment transport. I think it's very interesting. So to conclude all what I wanted to say about the Weser dunes, in the Weser Estuary, we have some low-angle dunes with varying asymmetry. And the dunes are more ebb asymmetric in terms of high discharge than in terms of low discharge. And we have some variations of the presence and properties of steep face and properties. And those properties are varying spatially along the estuary and temporally as well. So with the ebb and float phase and low and high discharge. So we cannot assume that roughness is going to be the same along the whole estuary all the time. And yeah, the morphology of the tidal bed form seems to be quite pointy like that. However, I know that in marine environment, we find all kinds of different dunes. So that's what I'm very interested now, to look in deeper marine environments, in continental shelf and even deeper, what kind of shape we have. I think that's super interesting. That was in terms of the science. Now I just want to tell you another 2 minutes here, Paul, about geomorphica. We're in the process of launching a diamond open access journal in geomorphology, and that is a journal which is free to access, free to read, and free to publish for all. Why do we talk about diamond open access? We have different types of journals where we can publish our work as scientists. And the most classic journals are the subscription journal. And that is where the university are basically paying for us scientists to get access. But that means that there is a readership exclusivity, and a lot of people do not have access to those journals. Then there are the so-called gold open access journals, which are really great. They are free for readers. However, the authors pay article processing charges, which is quite a lot of money. And here in Germany, I'm super happy. The university pays this. I just have to click one thing and everything is taken care of for me. It's not the case for everyone. And a lot of people still have to really wonder, how can I afford to publish in such a journal? And then there are some green open access journals, and those are with conditions. And that means that a lot of people don't actually use them. Recently started the diamond open access journals, and those are free to publish and to read for all. Now we follow an initiative from other Diamond Open Access journal in geosciences. Maybe you've heard of some of them. There is Volcanica, Sedimentologica, Tectonica, Seismica. Volcanica is already here since 2018, I think. Tectonica is just open for submission. Sedimentologica and Seismica would like to launch this year. And now we come with Geomorphica. We're a bit later than the other four. We started in January with getting our name, and then we formed our commissions, and now we have a steering committee which got elected. We invited people to design a logo, and we had a friendly competition, and now we have a beautiful logo. And we're working at the moment to get an agreement with a university library to do our journal hosting, and we're in discussion about the journal funding. So next step is gonna be the big thing where we need to design the journal formats, create the website, elect editorial board and associate editors, and we're aiming to launch early 2023. I'm telling you this because we're actively looking for new members, and very specifically, we're looking to get diverse editorial board and associate editors. So for now, we have actually a lot of people from Europe, and a lot of mid to senior career people, and I would really like to see some early career scientists, some good gender representation, and not just people from Europe, people from all over. And you can bring us your expertise and your ideas. If you want to get involved, you can visit our homepage or follow us on Twitter or just get in touch with me. And that's it for me. Thank you very much.
Wow, Alice, this is fantastic. You know, I very appreciate to see that the dynamic of that river Bedform moving is so mobile, you know, with flooding ebb and plus the river import. This brings us such a big challenge for maintain the navigation channel. I mean, because no matter how much, you know, how hard your dredging is moving back, keep moving back. I mean, that's very significant. Okay, now is open floor for the audience to have. If you have any questions, please just unmute yourself, ask Alice directly.
Hi, Alice. Can you hear me?
Yes, go ahead, Chuang.
Hi, Alice. Thanks for the nice talk. My name is Chuang Jing. I have been working on standard repos with Giovanni Coco.
Yeah.
And it's a very nice talk. And I got two quick questions here. And the first one is how much longer the dunes migrate in a month or like in a year? Like does it migrate 10 meters or 100 meters in a month? And the second, you can answer.
Okay, I answer and then you ask your second question, because if not, I'm gonna forget. Yes, so I'll answer directly.
Yeah. It's okay.
We haven't calculated the migration rate exactly. I think it varies a huge amount depending where you are in the estuary, and that's the whole thing with the asymmetry of the dunes. I think those ones are not going to move very much, because in times of low discharge, they're moving upstream, and in terms of high discharge, they're moving downstream. So I suspect overall, they're not moving. Those ones will be moving a tiny bit, like, you know, maybe a few meters a year, I would say, towards the ebb direction, towards the sea. And those ones will be moving a lot. So it varies. It depends very much where you are in the estuary, the migration rate.
Okay, thank you. My second question is, so I noticed that in some paper people mentioned that they always observe ripples formed on the gentle side of dunes. But I'm wondering, did you observe this pattern so in your field work? And do you have any idea on what kind of situation this pattern forms?
Yeah, that's very interesting. We definitely observe, so not in the Weser Estuary because we don't have a very high resolution. Yeah, we have only 2.2 meters resolution, so it's low resolution. But then in the other places, like here, that's the tidal inlet that I was talking about. Here we have different types of dunes which form, and we have the very large ones. Here you can see the crest. That's the crest of a large one and the crest of another one. And then we have what we call secondary bedforms. And those are large secondary bedforms. And here you even have some smaller secondary bedforms. And I don't know if we were going then, because now that's still a 0.5 meter resolution, which is not high resolution enough to really get the ripples, I think. So I think if we would be able to observe them, we would even see maybe even more scales of bedforms. So it's difficult to say how many bedform scales are in there, and that is something people have a lot of different thoughts about that, and especially in rivers, people have come up with different ideas, but there is still some work to do, especially in tidal places, to look at the interactions of all the different bedform types.
Okay, thank you. Thanks a lot.
Thank you so much.
Nice. Next is Muriel Bruckner.
Yes, hello everyone. Thanks, Alice, for this really interesting talk.
Thank you.
I do numerical modeling of large-scale estuaries, and we have to parameterize the roughness. And then we're usually interested in if we have ebb or a flood dominant sediment transport, if we have importing or exporting estuaries for sediment. So when I now heard that these dunes change the roughness depending on if we have ebb or flood flow, I was wondering if you think that this will also have a large scale effect on the sediment transport directions, and if we have to incorporate this in our models to actually predict if we have flood or ebb dominant sediment transport.
Exactly. Do you know Gerald Herrling, maybe?
Also from Bremen?
Yeah, he's in Kiel now.
Ah, okay. That's where I'm from. So
yeah, exactly. That's why I asked you, because yeah, exactly. So Gerald worked on that, and he worked on that. I just put the link to his paper in the chat now.
Okay, great. Thank you.
Yeah, Gerald worked on that, and he worked on that especially looking at the hydrodynamics, but also he could definitely show that it has a strong influence on residual bedload transports.
Oh, okay, perfect. Thank you so much.
Yeah, he tried to parameterize this to put ebb, so to put the roughness only during the ebb or only during the flood or during both, and that has a strong influence. What is right or what is wrong, or how to go from the measurements of the dunes towards to the correct roughness, we don't know yet. Okay. But we know it has an influence.
Yeah, okay. Well, it makes sense.
Yeah, but not sure it helps a lot though.
Well, some future directions for research, I guess.
Exactly, yeah.
Okay, great. Thank you so much.
Yeah, thank you.
Okay, nice. Next, Valentine.
Yeah, exactly. Hi, Alice. I'm just going to turn just to again. First of all, thank you for advertising for the OS Journal.
Of course.
Just shut off my camera now, so you don't need to see my face. Yes, I come maybe from a more sedimentological background, so I have also two questions. The first one is, do you have any like little core, like push core data going through these dunes? Looking okay. So that was an easy answer, maybe.
Yeah. yeah, exactly. No, we don't, and it's very tricky to take any cores in there because they're sandy. So I mean, I know whenever we try to get sandy sediment to core, really, I mean, we have just surface sample with a box core. Like grab sample, yeah. But when we try to take a core, we get in the end, maybe 5 centimeters at the bottom, at the top, and that is not really helping. You can't see anything deep.
Okay.
Yeah.
And so that is already very good information. And maybe my next one is in terms of your distribution of asymmetry of your bed form, do you see a change in this distribution depending if you have neap tides or spring tides coming into the...
I haven't looked at that because we have only data around once a month, and it's not exactly the same through the whole estuary. You know, like it's not like once a month they do the whole estuary at once. Yeah, so I have very patchy data.
Okay.
So I haven't looked at that, but it's a good thing. I know I looked at so Gerald, that colleague that I was talking about, he has the model of the Weser. I looked at the hydrodynamics that he modeled, and there were changes depending on neap and spring tides, of course. And what I could see what I think is that the sediment is being transported only during spring tide. During neap, the currents are not really moving very much.
Okay. Yeah, super cool.
Yeah,
that's all
thanks.
from my side.
Thank you.
I think Valentin is a very good question. You know, you can ask a student to do a project, compare that. You know, how much exactly the spring tide can, you know, compare the regular and neap tide. And other scenario is the storm. I'm not sure is any tropical storm really coming to the Weser Estuary, maybe not really, or maybe winter storm or anything.
Yeah, so we get some storms. Sometimes we don't have a lot of influence from the waves because they don't really enter, you know, they're blocked before really entering the estuary, but we get storm surges. Yeah, that's when we get flooding in Bremen. Then if there is a high tide and a storm surge, the dikes get flooded, here. And that is something that we would like to look at as well. That is because that's going to change the hydrodynamics definitely a lot. And I think there is an influence. Gerald was also talking a lot about, the effect of wind, really, because it's the wind which is pushing the water, which is making those storm surges. So he wanted to look at that.
Nice.
Another thing that we're looking at as well is the variations on the side, because now I told you a thing about like as if the estuary is always the same on the side, but of course you get variation, especially whenever you have a meander or like, you know, a little curve in the channel. You don't have the same dunes on each side of the channels, and that is something which I think is quite interesting as well. There is still so much to do.
Okay, so I saw you done a series along the channel survey, you know, mainly the Bedform and Saskan. So do you have any cross the channel like periodically survey, not only the Bedform, but also maybe do a little bit chip profile? Then you can see how the bedding, how the stratigraphy change over time.
Yeah, exactly. That I don't think I have in the Weser. I know that we have punctually here or there we have done some surveys, and my colleague Marius Becker worked on that a bit. But we don't have that data as with high resolution like we have the bathymetry.
Yeah, that would be good. You know, even a small chip. And near the Bremen, you know, you can do a couple cross session just every month. Just go there, both do a couple. Yeah, then you can compare.
I will talk to the authorities to see if they want to do that. Yeah,
try to get more.
A lot of things. Yeah,
get more fun. Very nice. So, anybody else? Anybody have some questions? Okay. So Alice, thank you very much. Also that particularly also the diamond open access option. I'm looking forward to it. That's very good.
Exactly. Please, everyone, feel very welcome to tell us your interest. And as I said, we are especially looking for early career and any kind of diversity that you can bring is very appreciated in our journal.
But one thing I just not remind you, but maybe a suggestion, you know, the big challenge now is to try to get a review, and people accept the invitation of review and finish the review on time. You know, even including ourselves, sometimes we also delay the process.
I'm late for a review. Tell me about it. Yeah, I'm
Yeah.
late. I know it's on my list of things to
So,
do. Exactly, that is true. And I think it's also maybe because I've got the feeling maybe only always same people are asked for reviews, because it's people
Yeah.
who are well known and who are already senior. And why can't we ask more, early career
Oh, definitely.
people? And people from all over the world, like, is there a reason why African scientists can't review papers? Yeah,
I tell you, the senior people decline the invitation more than junior colleagues. But I have an idea for your reference. I have this in mind for a while, but never really take action. And maybe we can think about some academic credit system. And if people accept to review a paper or anything, and if they can finish the review within 1 month, and we can give them academic credit, and they can use that academic credit to attend a conference, registration, buy books, subscription. I mean, it's a sometime when we review some work, some community work, we get a little bit reward, but that I don't know is a controversial thing, but it's sometimes with a little bit incentive could help people feel obligation to finish the review on time.
Yeah. I agree. Yeah, I think it would be good. Anything which would help people to accept review and to do it in a good time would be great. Yeah. That's, I will. You know what? I have put it down, and I will bring it to when we draft all our. We have to do that. So
yeah, if you have that open access new journal, maybe think about new way and something like this. If I'm an author, if I submit something, I may be willing to pay a little bit extra money and put into that system. Then the journal can use that little bit money like award for those can finish the review quickly, accept the invitation and return the review in time. And in this sense, they will be speed up the whole process. And even for example, if people give you willing give you $100 for review a paper, I think most of people will feel, oh gosh, accept the money, I had to finish. I know it's bad. I mean, it's very bad. We should not do this, but the reality is very
So we are free for all, and we're not paying anyone, but to get things for regarding conferences or things like that, that is definitely a good idea. Yeah. Some kind of reward, which is something else than money.
Yeah. I mean, the credit is that credit is the only you cannot buy beer, but you can pay registration. You can do you just for academic purpose.
Yeah.
Some company can do this. Maintain an academic credit system.
Yeah, Valentin, je suis 10 reviews and get a coffee mug, says Valentin. Yeah, I agree with that.
Okay. Alice, thank you very, very much. And
thank you so much.
It's a fantastic, to hear your talk. But encourage more, as you mentioned, please encourage more postdoc, young colleague, to contribute talk. I mean, I think now this the talk now become much valuable because great.
Yeah.
Okay, I think I need to thank you again. Okay, I'll see you some of you next week. Okay, bye-bye.